So now that we've discussed ionic compounds, we will now talk about what happens when two nonmetals form covalent compounds. In the previous chapter, we saw that two ions can come together, one with a positive charge and with a negative charge to form ionic bonds. And this can be represented again here below that we have cesium and bromide that are going to come together. Cesium is going to donate an electron to form this positive charge, and bromine is going to gain an electron to form this negative charge. And these negative and positive charges are attracted to each other to form cesium bromide here. And this is what it would look like as an electron configuration. This is shorthand xenon with a 6 energy shell with one s electron. And this is that noble gas here, the closest noble gas to cesium. So it's going to lose this 1s electron and it's going to look like xenon. For bromine, we have argon and it has this 4s2, 3d10, 4p5 electron configuration here. And when it gains an electron, it's now going to have 6 electrons in this p orbital. So we're focused on this 4 outer energy shell. It already has a full s orbital, but it needs one more in this p orbital. So when it has 6, now it's going to look like its closest noble gas configuration to form krypton. So this is just a summary, one slide to summarize what we talked about in our last chapter. But what are now going to talk about is what happens when we have two nonmetals that have similar electronegativities that are going to form a bond. So we're now going to talk about the Lewis octet rule. And in 1916, G. N. Lewis recognized the stability of elements who have achieved noble gas configuration. And he articulated this in his octet rule. Atoms tend to combine to achieve the noble gas configuration of Ns2 and Np6 to have 8 valence electrons. And your valence energy shell electrons are those that are in that outer energy shell. So for group 1 and 2 elements with low ionization energies, so those are our metals, and group 6 and 7 elements with high electronegativities, so these are our nonmetals, noble gas configuration is achieved through electron exchange. So that's what we talked about in chapter 3, where we had our ionic bonds forming. But for this chapter, what happens about all the other elements? They don't have low enough ionization energies or high enough electronegativities to do either. They can't lose or gain. So instead, they choose to form molecules through electron sharing. So when we talk about ionic bonds, we oftentimes talk about them as compounds or as salts. But when we talk about covalent bonding, we're going to be describing them as molecules. So a molecule is a group of chemically bonded atoms that has the characteristic properties of a substance. Atoms of elements bond in order to obtain a noble gas electron configuration. We can have molecules that are made up of just one element. So this is called diatomic hydrogen. It exists as H2. And some molecules are made up of different elements. So this is water, which has H2O, 2 hydrogen atoms, and then 1 oxygen atom. So what I alluded to in the last slide is that what we call these molecules are diatomic molecules. These are elements that exist naturally as molecules in nature because they contain 2 atoms of the same element. So this is a hydrogen, oxygen, nitrogen, fluorine, chlorine, iodine, and bromine. These exist naturally in nature as these diatomic molecules. Some elements also exist as molecules, but they're not diatomic. So you can see here, this phosphorus doesn't have just 2, it can exist with 4, and the same with sulfur. It can exist with 8 sulfur molecules together. You can have molecules of different elements, and to determine how much of each element is found in a molecule, we depend on the subscripts. And this, so here when we look at water, we have H2O. The subscripts are the little numbers at the bottom. This is telling us that there are two atoms of hydrogen and one atom of oxygen. For carbon dioxide, that we can see that we have, if there's no subscript here, we just know there's a 1 there. So this is telling us that there's one atom of carbon and two atoms of oxygen. And the unique combination of elements give the compound its unique properties. So covalent bonding is the shared pair of electrons. And a molecule is a group of atoms held together by covalent bonding. So this is what a water molecule would look like in terms of its outer shell electrons. We have two hydrogen molecules, as we said. H2O is the molecular formula for water, and it has one oxygen atom. And through a chemical reaction, you can have the formation of a new compound. We have these two hydrogen atoms that come together to form this oxygen, with this oxygen molecule to form water. And if we count up the electrons that are now in this outer shell, these valence shell electrons, we can see now that the last energy shell of each atom in this molecule is full, thus giving it a noble gas configuration. So hydrogen has one energy shell, and it can, with an s orbital that can hold two electrons. And when it shares with oxygen, it went from having one electron in its energy shell to now having two, which makes it look stable like the noble gas helium. This is true for both of these hydrogen molecules, atoms. When we look at oxygen, it now has 8 when it shares. So 1, 2, 3, 4, 5, 6, 7, 8, which makes it more stable and looks like it's closest noble gas than when it had 1, 2, 3, 4, 5, 6 prior. So this is now a stable molecule. And molecules that are bonded covalently have obtained noble gas configuration by sharing. So on the previous slide, we saw hydrogen atoms share an electron with an oxygen atom, and this results in the following electron configuration: 1s2 for the hydrogen and a 1s2, 2s2, 2p6. And you can remember and recognize this ns2 NP6 that is found common to all the noble gas configurations. So notice that hydrogen and oxygen achieve their noble, the electron configuration of the noble gas that's closest to them. For hydrogen, that is helium, and for oxygen, that is neon. So now that we kind of have an understanding of how two atoms can share electrons to form a bond, we have to talk about different types of covalent bonds. So we can have a polar covalent bond and non-polar covalent bonds. Polar covalent bonds are formed between elements with different electronegativities, and therefore the sharing of electrons is unequal. The element with the higher electronegativity is considered partially negative, and we will denote that using this symbol here. It's like a little S type symbol with a minus. And then the element with the lower electronegativity is considered partially positive. So this is the same symbol with this little plus sign. So positive and negative, partially. And we can tell which atoms have the have higher electronegativity than the other based on those periodic trends that we discussed in our first lecture. Non-polar covalent bonds are formed between elements of the same type which have identical electronegativities. Therefore, the sharing is completely equal. So now we're going to talk about how we can draw the covalent molecules that we discussed. And we're going to do this first by understanding Lewis dot symbols. Lewis dot symbols are used to represent the valence electrons of an element. Each side of the element represents electrons in the S and P subshells, although they do not necessarily have to be in what order that is depicted here. So this X is going to be where we put our atom. Let's say, for example, we have oxygen. And then we are going to put the electrons that are in that valence, that last energy shell around it. So here, let's say we have a noble gas, and it's going to have a full outer shell of electrons, which should be 8. So we put 1, 2, 3, 4, 5, 6, 7, 8. And this here is some instructions on how to draw an electron dot or a Lewis dot structure. So step 1 is to identify the symbol for the element and its number of valence electrons using the periodic table. Step 2 is place the corresponding number of electron dots around the symbol. Imagine that the symbol has 4 sides, a top, right, bottom, and left. Begin by assigning 1 dot per side first, moving clockwise around the symbol. Then, if there are still more dots to assign, start adding a second dot to each side until all the valence electrons have been accounted for. So here are some common Lewis dot structures based on their placement in the periodic table. Here, let's say for oxygen, for example, it has 6 valence shell electrons. So we use the symbol O here, and now we're going to fill in those electrons. We can symbolize them by putting dots. So we'll first want to fill them in singularly first. So we'll put 1, 2, 3, 4, and because we have 2 left over, we'll then go in to fill in the rest. So we'll put 5 here and 6 here. And that way we know that there are 2 empty spaces left that need to be filled with electrons. So those are Lewis dot symbols, but we want to also use this to represent how molecules are formed as well. And so we'll do that using Lewis dot structures. In a Lewis dot structure, we are essentially trying to fill in the missing dots for each element through shared electrons. When drawing them, you can arrange Lewis dot symbols for each element such that lone electrons line up and can then be shared. So by lone electrons, we mean like here in this example, these are lone electrons. These are can have and should have 2 electrons here, but they're by themselves. And a shared pair of electrons, a bond, can be represented by a straight line. And I'll show you what that means in this example here. So we're going to use the example of water. The Lewis symbol for hydrogen is this H symbol that we get from the periodic table, and it has 1 valence shell electron, which is denoted here by this red dot. And we have 2 of these hydrogen atoms. We have oxygen, as we've seen on the previous slide, that has 6 valence shell electrons, and it has 2 of these electrons or shells that are not, subshells that are not full. These are 2 lone. Now they're going to form a covalent bond, and we're going to line up these molecules in a way that these lone electrons can now be exposed to each other and bond. So when we form a covalent bond, we have our hydrogen. It's going to bring an electron with it, and it's going to take one from oxygen. So these 2 here, and it's going to form this bond here. And for this hydrogen, it's going to take its lone, and it's going to share it with oxygen, and it's going to form this bond here. And we can and replace these 2 shared electrons. So shared electrons are the electrons that are between 2 atoms, and we can replace those with these solid lines. So we see here the same example with this nitrogen and 3 hydrogen. The nitrogen has 5 valence shell electrons, 1, 2, 3, 4, 5. So it actually has 3 electrons that exist in their orbitals alone. It's going to share its electrons with hydrogen that has its 1 independent electron. And when these come together, you can see that you form 3 bonds. This is a bond here. The hydrogen and nitrogen are sharing here. They're sharing electrons here, and they're sharing electrons here. We can go ahead and put a dashed line in. So covalent bonding always involves shared pairs of electrons. Electrons are never shared in odd numbers. So you're never going to see 3 electrons here or 1 electron here. There must be 2 electrons in each bond. Electrons that are not shared between atoms but are only orbiting one atom are known as non-bonding electrons, or we can also call these lone pair electrons. So this is different than a lone electron, which is one electron by itself. We're going to talk about a lone pair. And so this means that it is not actively participating in bonding. This is shown here where we have fluorine that has 3 pairs of electrons that are non-bonding. But we do have 1 pair of bonding electrons here. And this is participating in the bond. And if we were to write this with a line, we could put a line here. So we'll take another look at water, for example. It has 2 hydrogen atoms that are sharing electrons with this 1 oxygen. And this is our Lewis dot structure, where we see that each atom in this molecule has now a full valence shell. 1, 2, 3, 4, 5, 6, 7, 8 for oxygen. And then for the hydrogen, it needs 2. So we see that each hydrogen here has 2. But that being said, we have 2 pairs of electrons that are not participating in bonding. So as we saw in the previous slide, these are non-bonding pair of electrons, and this is a bonding pair. So in water, there are 2 bonding pairs and 2 non-bonding pairs, and we can put a line here to show that this is a bond between the hydrogen and the oxygens. Typically, covalent bonding is between 2 non-metal elements. It can occur between metalloids and non-metal elements. And to reiterate again, the shared electrons are represented by a solid line. So this is what water would look like if we just put a line where those 2 shared pair of electrons are. And when you do draw this molecule, you do still need to show that you have these non-bonding electrons here. So there are different types of covalent bonds. Electrons can be shared in different number of pairs. So I do want to say pairs is 2. So there are still 2 electrons in each bond. When 1 share is paired between 2 atoms, we have a single bond. When 2 shared pairs exist, we have a double bond. And when 3 shared pairs exist, we have a triple bond. And remember, the end goal is to give each atom 8 valence electrons. So here are some examples of some different types of covalent bonds. We are going to look at carbon dioxide as an example here, where we have our Lewis dot structure for oxygen, which has 6 valence shell electrons. We have our Lewis dot structure for carbon, which has 4, and then we have another oxygen, which has 6. And if you just put these together the way that they are with a single bond in between these oxygen and carbon molecules, atoms, you would not have 8 electrons around. So let's just take a look. Let's say we have a bond here and a bond here. We'd have 1, 2, 3, 4, 5, 6 around oxygen. We'd have 7 around oxygen. We'd have 1, 2, because these are going to be shared, 3, 4, 5 around carbon, and it's going to share here, so that would be 6. And then we'd have 1, 2, 3, 4, 5, 6, 7 around oxygen. And 7 and 6 and 7 are not an octet. We need 8. So in order to do that, we're going to now take these additional electrons, and we're going to move them into the center to form a double bond. So a bond is 2 electrons, and if we now have 2 pairs of electrons, we have a double bond. And if you count up the electrons that are now being shared around each molecule, we can get 8. So let's see. We're saying this oxygen is sharing these electrons, 1, 2, 3, 4, 5, 6, 7, 8. This carbon is now going to be sharing all of these electrons. And if it helps when you're drawing these out, you can actually draw a circle around what's being shared, kind of similar to what a Venn diagram would be. And you have 1, 2, 3, 4, 5, 6, 7, 8. So this carbon is now happy with 8, and the oxygen is going to be sharing these electrons between this carbon and this oxygen. That gives us 1, 2, 3, 4, 5, 6, 7, 8. So how we can now, for each shared pair of electrons, we will draw a bond. So this oxygen and carbon have a double bond. There are 4 electrons represented here. 1, 2, 3, 4. And this carbon and oxygen also share 4 electrons and can form a double bond. 1, 2, 3, 4. So take some time to go through each of these examples here. You'll see that you can form double bonds, triple bonds here, excuse me. So when you have triple bonds, that means you're sharing 6 pairs of electrons. 1, 2, 3, 4, 5, 6. And because you have 2 that will make 1 bond, you're going to form a triple bond in between these 2 nitrogen atoms. So one way that you can predict the number of bonds is to take 8, which is the amount of electrons that each atom wants to achieve, and you can subtract that from the number of valence electrons. So group 7 elements, remember the groups are the columns going down, and on most periodic tables, it will have the group numbers on the top of each column. Group 7 elements will form 1 bond. Group 7 elements have 7 valence shell electrons. So we're going to take 8 minus 7, and that's going to give us 1. Group 6 elements will form 2 bonds. So 8 minus the number of valence shell electrons will be 6. That's 2. Group 5 elements will form 3 bonds. 8 minus 5 is 3. And group 4 elements will form 4 bonds. 8 minus 4 is 4. So this is an easy way to kind of figure out how many bonds are going to form based on where the element is positioned on the periodic table. So here is a helpful video on your own time. I encourage that you visit this link and see just another example of Lewis structures and how we draw them and form molecules with them. So here is just an overview of what I shared in the previous slides, that if you want to draw Lewis structures, you count the valence electrons. You can either use the group number, or you can write out the electron configuration and figure out how many electrons are in that last shell. And if you have a charge, add or subtract the electrons appropriately. So that's if you have a +1 or a -1, we learned how to use that to understand how many electrons are in that atom. Put the first element in the formula in the center. Connect all the atoms to the central atom with the single bond. So for example, when we had water, we used oxygen as our central bond, and then we had the 2 hydrogens on the outside. Determine how many electrons you need to draw those single bonds in step 3, and subtract those from the valence electrons in step 1. And these are the electrons that you have left to work with. And then you want to distribute them as lone pairs to all the atoms, starting with the outside atom. If you don't have enough for the central atom, create double or triple bonds as needed. So again, we're going to do some practice, and you can take some time to draw the Lewis structures for the following. Pause the video and give it a try. So this is what your answer should look like following those steps below. And we can count up how many valence shell electrons. I'll use this top molecule as an example, and then you can compare your answers with the rest of the answers below. So the number, hydrogen has 1 valence shell electron and fluorine has 7. So let's add up the number of valence shell electrons. That will be 8. And then we are going to see that they're distribute those electrons between the two molecules. So we'll have F as our central, and then we'll add 1, 2, 3, 4, 5, 6, and 7, 8 around that central molecule. And that hydrogen is going to be sharing the two atoms with the fluorine. And that's going to result in this final compound here. And if we take a final look at the number of electrons now that are being shared between the two atoms, we have hydrogen that now has 2 electrons and fluorine that now has 8 electrons. And so those two outer shells are full, and the molecule allows each of these atoms to have a noble gas configuration. So there are some exceptions to the octet rule. We'll briefly discuss some of these. We will go more in detail into what happens when we have an incomplete octet, an odd electron, and then an extended octet. So let's look at bromium trifluoride. If you were to make a Lewis structure, you would need to create a double bond between boron and trifluoride. This would mean that the most electronegative element, fluorine, is going to share an additional pair of electrons with a very low electronegativity element, which is boron. This will create what is known as a formal charge, or an element sharing more electrons than it usually would. This rarely happens, and certainly will not happen with a low electronegativity element. So instead, to create this compound, we just accept that boron will not achieve an octet. And that can be seen here in this Lewis dot structure for bromium trifluoride below. So we can count that fluorine does have its appropriate number of electrons to have a noble gas configuration: 1, 2, 3, 4, 5, 6, 7, 8. Again, because each bond represents 2 electrons. And but when we count 1, 2, 3, 4, 5, 6 for boron, we can see it only has 6. And because we don't want to put a formal charge on those elements, we're just going to accept that boron is going to have an incomplete octet, so it has 6 instead of 8. When we have an odd electron situation, we'll look at nitric oxide, or NO. And if you were to draw the Lewis structure for nitrous oxide, you will find that you have 11 valence electrons. And that's an odd number. If we had a bond, we know that each bond has 2. And so because we have this odd number, there is no way to obtain an octet here. So because nitrogen is less electronegative than oxygen, it will not achieve an octet. So we can see that this nitrogen here has 1, 2, 3, 4, 5, 6, 7, but the oxygen does have a full octet: 1, 2, 3, 4, 5, 6, 7, 8. So it's similar to the incomplete octet, but this is not because we have, this is because we have an odd number of electrons. Then we have an expanded octet. So this is sulfur hexafluoride. You have more electrons than you need to give each element an octet. So in the last example where we didn't have enough to give one, we had an odd number and couldn't give a full octet. This, we have more electrons than we need. So for elements that are in the 3rd row or below, we must remember that we have d orbitals. So when we think about the octet rule, we're typically thinking about the s and p orbitals. But when we do get to that 3rd row where we enter our transition metals, we have d orbitals which can hold additional electrons. So we assign the additional electrons to the central atom. So sulfur will have that d orbital, so we can now allow this to hold more than 8 electrons. So the fluorine here is stable because it has 1, 2, 3, 4, 5, 6, 7, 8, but we have 1, 2, 3, 4, 5, 6 bonds. And if each bond has 2 electrons, 6 times 2 equals 12. And so this has more than an octet, but that's fine because we have d orbitals that we can put those electrons in. So now that we've talked about bonding and some exceptions to the octet rule, we'll now talk about resonance. What do we do when we need to create a double or triple bond and we have multiple options that are all equally good? Well, we write them all, because when there are multiple options, the molecule will not choose any one structure, but will form a hybrid. So we will do an example of this. And we have to remember too that electrons don't exist in a very static formation. They are in electron clouds and they're constantly moving. So it wouldn't be accurate to just depict one formation. Resonance allows us to depict all the different types. So for this CO3 with a 2- charge, here we can see that there are multiple ways that we can draw a double bond. So we have this first configuration here, and we can have the double bond on the right, but we can also have an equally good structure with the double bond between the oxygen on the left. And then because we have 3 oxygens, you can see that we can also have this double bond on the bottom. And one is not more right than the other. We need to represent that this molecule will exist probably in all 3 formations at some period of time. So what we're going to do is draw a resonance structure, which we're going to show using this type of symbol below. So we have our carbon in the middle and our 3 oxygens on around the central atom. And then we're going to have a solid line here, but because we can have the double bond here, here, and here, we're going to show that by these dotted lines. These dotted lines represent where that double line could be. This resonance structure represents all 3 of these possibilities here, so you don't have to write them out independently. So that is resonance structure. And now we're actually going to name these covalent compounds similar to how we named our ionic compounds. Naming covalent compounds is different because there are more ways that nonmetals can combine. We identify the number of each using a prefix. So these are some common prefixes from 1 to 10. Mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. And if you have one atom, you would put mono in front of it. So this example, NO, is nitrogen monoxide. And you don't have to put the mono in front of nitrogen here. You can have nitrogen dioxide. So the dioxide is referring to the fact that this subscript here is showing us that we have 2 oxygen atoms in this compound. Here, if we're following the oxygen, we can use this tri prefix for 3. And the nitrogen in this compound also has 2. So we could call this dinitrogen, meaning 2 nitrogen, trioxide, which is 3 oxygen here. And there are more examples. You can keep going and going. So in addition to resonance structures, we also need to talk about molecular geometries. So now that we know what the arrangement of the electrons and bonding, we need to determine the shape of the overall molecule. So the way that we draw molecules are in a very one-dimensional space, but we exist in a 3-dimensional space. So therefore, there's some shape here. The underlying principle to remember is that electrons will repel each other. So the overall shape of the molecule will be determined by the geometry that keeps the electrons involved in bonding as far apart as possible. So, we're bringing these electrons together, we're sharing them, but each electron has a negative charge that will naturally repel the other. So what a molecule is going to do is arrange itself in such a shape that keeps those electrons as far apart as possible. So for the purpose of this class, these are some common molecular geometries that you will see. And we're going to look at the number of electron domains. We're going to look at the number of bonding electrons and non-bonding electrons, and that's going to share with us, help us understand what molecular geometry that we have. So for a linear molecular geometry, we have two electron domains here. That is shown in this diagram in the second column. There are two sets of electrons, and so there are two domains. We see that there are two bonding sets of electrons, and we don't have any non-bonding. So all the electrons in these domains are participating in bonding. And so when we have two bonding domains and zero non-bonding electrons, we form a linear structure. This has a molecular geometry of 180 degrees, or a straight line. An example is carbon dioxide. So we have this central carbon atom here, and we have these two oxygen. And you can see that these electrons are very, very far apart from each other. This linear conformation is a way that we keep these bonding electrons apart. So next we're going to look at what happens when we have three electron domains. We're going to use boron trifluoride as an example. So we have three electron domains. They're represented here in this diagram. Their three domains are participating in bonding. So we're going to form this trigonal planar geometry here. That means that we have electrons here, here, and here. And that is the way that we keep all of these electrons as far apart as possible. Now, in this trigonal planar shape, we also have what we call a bent structure. And the difference in this is that instead of three bonding domains, we have two bonding domains and one non-bonding domain. So an example is nitrogen dioxide here. We have in our Lewis structure that we have this oxygen, there's a double bond that's formed. So these are our bonding domains here, but we also have this lone pair of non-bonding electrons here, but and that we still need to make sure that they're as far away as possible from these electrons here. And in order to do that, we have similar to a trigonal planar, so still this shape, but instead of having a bonding domain at the top, we have these lone pair of electrons. So this is called a bent molecular geometry. If we did have bonds here, we would have a trigonal planar. Next, we're going to have our tetrahedral arrangement. This has 4 electron domains here represented in this domain diagram, and we have 3 different types of molecular geometries that can be underneath this tetrahedral domain. When we have 4 bonding domains or bonding electrons and 0 non-bonding, we have what's called a tetrahedral arrangement. So here we can see if we have carbon and 1, 2, 3, 4 hydrogen, they're going to have this tetrahedral arrangement where you have the hydrogen at the top, and then these 3 are going to be at the bottom. And we will probably talk a little bit more about the distance between each of these, but this is 109.5 degrees between each of these domains. Next, we're going to talk about trigonal planar, and this is going to be kind of similar to our bent structure. As you can see, we have 3 bonding domains and 1 non-binding. And so this non-binding here is going to be at the top, similar to our bent, and then we have these 3 bonding domains at the bottom. Then we're going to have a bent tetrahedral type of molecular geometry. So here we have two bonding domains and two non-bonding domains. So instead of having this bonding domain here, we have these lone pair of electrons, but we still are going to have what looks similar to this tetrahedral type of structure because these electrons need to be kept as far away as possible. As these two. And water is an example of this bent structure because we have these two lone pairs of electrons that need to be kept separate from these hydrogen atoms. So that will be it for today's lecture. We will go more into molecular geometries and how these molecular geometries can impact intermolecular forces in our next lecture.